Hello everyone, welcome to lesson 9-4, simulations. We will continue to answer the question, how can you predict the outcome of future events? And for our vocabulary today, we're going to use the word simulation. Real world link, music downloads. A new electronics store is opening up at the mall. 1 out of 6 new customers will receive a free music download. The winners are chosen at random. On Monday, the store had 50 customers. You can act out or simulate 50 random customers by using the random number generator on a graphing calculator. Type in the following keystrokes to set 1 as the lower bound and 6 as the upper bound for 50 trials. So here's the keystrokes. We have the left arrow, 51, 6, 50, parentheses, and you hit enter. The screen should look similar to the screen shown below. So at random intervals, we have 1, 6, 50. And when you hit the enter, you get all of this from numbers 1 to 6 at randomly at 50. Okay, and here's our first example of our first sample. 1, 2, 3, 4, 5, 6, 7 of the first 7 customers. So a set of 50 numbers ranging from 1 to 6 appears at random. Use the right arrow key to see the next number in the set. So if you use the right arrow key, you'll see the next few numbers. Okay. Let the number 3 represent a customer who wins a free download. Write the experimental probability of winning a download. So if the number 3 is the customer who's going to win a free download, just based on this picture that we can see that number 3 has won 3 times in the first 7 trials. 1, 2, 3, 4, 5, 6, 7, right? They've won 3 times. So the winner is 3 for every 7. Okay? At this point. Now, let the number 3 represent the customer who wins the free download. Write the experimental probability of winning a download. There it is. Now, as you know, we only took it from 7 because this is just an image and we can't hit the right arrow key. And you also know that the more you try it, right, the more the difference it will be. So maybe for the next 7 numbers, there was no 3. But this is the sample that we have, so that's what we're going to work with. The experimental probability is 3 out of 7, right? 1, 2, 3. Or we could say about 43%. Okay, that's actually a really likely probability of winning, right? It's almost half the time. All right. Compare the experimental probabilities found in exercise 1 to the theoretical probability of winning download. So then, let's just see. The numbers are 1 to 6, right, everybody? 1 to 6. So how many times could I get one number? It's 1 to 6, right? So theoretical, you can say 1 for every 6. And the theoretical probability is 1 of 6, or about 17%. So we just looked at a simulation done for us by a calculator, and we were able to figure out, or at least get an idea of the percentages. So what is a simulation? A simulation is an experiment that is designed to model the action in a given situation. For example, you use the random number generator to simulate rolling a number cube. Simulations often use models to act out an event that would be impractical to perform. Okay, let's take a look at the first example. A cereal company is placing one of 8 different trading cards in its boxes of cereal. If each card is equally likely to appear in a box of cereal, describe a model that could be used to simulate the cards you would find in 15 boxes of cereal. Now we need to try it 15 times, correct? Try and let's just see the probability. So we need to have 8 different outcomes. Well, when you take 3 coins and you throw and you compare all the different combinations of heads or tails that you could have between the 3 coins, we actually get 8 different outcomes. So you can have heads, 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 tails, heads, tail, head, 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 tail, 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 head, tail, head, tail, and so on, and then tail, head, head. So you can see that we have 8 different outcomes. If we were to throw these 3 coins up, we could use this as a tool or to model 8 different outcomes. Okay? So for example, the outcome of all 3 coins landing heads up simulates finding card 1. Toss 3 coins to simulate the cards that might be in 15 boxes of cereal. Repeat 15 times. So let's just say I decide I throw up all the coins and I get heads 1 time. Okay? That would be card number 1, sorry, when I get head. When I get head, tail, I get card number 2, and so on. You see? So then we would just practice throwing up these coins, and we would see how many times I would have to throw them up to get all 8 cards. Now remember, head could repeat multiple times in the times that I'm throwing up. So that means I would get card 1 multiple times. I'm sure if you've ever gotten any kind of prize in a Happy Meal or in a box of cereal, you've gotten the repeated prizes. For my son, I get him Kinder Surprises, and we try to collect a lot of the same ones, but we keep getting the repeated toy. So let's try it ourselves. A restaurant is giving away 1 of 5 different toys with its children's meals. So 1 of 5. So there's 5 different toys. If the toys are given out randomly, describe a model that could be used to simulate which toys would be given with 6 children's meals. So 6 children's meals. Because we have 5 different outcomes, right? 5 different outcomes with 6 trials. What we could use is a number wheel, or we could use a number wheel where we divide the wheel into 5 different equal parts. So it would look like that. Now this kind of looks like an orange, but we would number it 1, 2, 3, 4, 5, and in the middle we'd have our spinner, right? Our spinner. And we would spin that. Now it's like an arrow, okay? And we would flick it, and we would flick it 6 times, right? To simulate the toy. So we have toy 1, toy 2, toy 3, toy 4, toy 5. Flick it, and we would see what toys. Now this would simulate what equal opportunity over here for all 5 different toys. Now, boys and girls, this is all experimental probability. Right now, we're just identifying different models or different tools that we could use to test these or simulate these situations. This would be one. So again, if you find that you're not really writing anything down, it's because we're not really doing any math yet. We will be practicing these in class. Feel free to draw this number wheel for this scenario. The purpose of this video is to get you thinking about tools that we could use to model. Now here's another one where they use a wheel again, but this time with colors. Every student who volunteers at the concession stand during basketball games will receive a free school t-shirt. The t-shirts come in 3 different designs. Design a simulation that could be used to model this situation. Use your simulation to find how many times a student must volunteer in order to get all 3 t-shirts. So let's just pretend there's a red shirt, a blue shirt, and a yellow shirt. Now these don't have to match the colors of the shirt. We just have to have 3 clear outcomes, right? Use a spinner to divide into 3 equal sections. Assign each section to one t-shirt. Spin the spinner until you land on each section. So you'll keep doing it until you land on all 3, and that'll give you an idea of how many times you must volunteer to get each shirt. So first spin, blue. Okay, so we got that guy. Second spin, oh, the other shirt. Third spin, we go right back to blue. So the first time you volunteer and the third time you volunteer, you get the same shirt. And then the fourth time, you got lucky and you got the third shirt in the combinations. So for this trial, it took 4 times volunteering. You have to volunteer 4 times to get all 3 shirts. Therefore, based on the simulation, a student should volunteer 4 times in order to get all 3 t-shirts. Okay, let's try this together and see if we can identify what would be a good tool to recreate the simulation. Mr. Chen must wear a dress shirt and tie to work. Each day he picks one of 6 ties at random. Design a simulation that could be used to model this situation. Use your simulation to find how many days Mr. Chen must work in order to wear all his ties. Now it looks like we have 6 different outcomes. Well, what has 6 different outcomes? A die, right? A number cube. This would be a good tool to use because you have 6 equal outcomes. You throw it up at random, you might get a 6, you might get a 3, you might get a 5. Now, these numbers are assigned to each type of tie. The 6 could be his red tie, the 3 could be his blue tie, the 5 could be his green tie, and so on. And you're going to throw the number cube, or the dice, up as many times until you get every number once. Now again, we're not actually doing the experiment. We're just going to use a tool. This is the tool we would use. We will do these experiments in class. Simulations can also be used to model events in which the outcomes are not likely. For example, predicting the weather. Here's an example. There is a 60% chance of rain for each of the next 2 days. So each of the next 2 days. So Monday, 60% chance of rain. Tuesday, 60% chance of rain. Describe a method you could use to find the experimental probability of having rain on both the next 2 days. So experimental probability. What you could do is you take 5 marbles, right? You take 5 marbles, 3 red and 2 blue marbles. The 3 red will represent the 60%, right? 20, 40, 60. Each marble is 20%. And then 2 blue marbles to complete, right? This would be your 80% and your 100%. But your 2 blue marbles in the bag. Let 60% or 3/5, 3 out of 5 marbles of them represent rain. So they'll be, and then let the 40% or 2 out of 5 marbles represent no rain. Randomly pick 1 marble to simulate the first day. So you have all the marbles in there. The 3 reds and the 2 blue. And you pick out 1 marble. Then let's say you pick out a red one. Then it means that day is going to rain. You throw it back in. You replace the marble back in the bag and pick again to simulate the second day. Find the probability of rain on both days. Okay, now let's try one ourselves. During the regular season, Jason made 80% of his free throws at basketball. Describe an experiment to find the experimental probability of Jason making his next 2 free throws. So, again, we would take marbles. You can make 4 out of 5 marbles, which represents 80%, right? These could be, let's just make these the red ones. Okay, and 1 out of 5 marbles, which is the other 20%, this is him not making. So he made 80% of his free throws. So the red marbles, if he picks out a red marble, it means he makes the next throw. If he picks out a blue marble, it means he doesn't make it. So then you put all these marbles in, all 5 of them in there, and you pick out one and then put it back in, and you pick out the next one and you put it back in. And that's your experimental probability. Theoretical probability doesn't work like that, though. In theoretical probability, we'd have to actually multiply our outcomes. But I will explain that more in class. So the objective of this lesson was to identify ways or tools to simulate real world experimental probabilities. These are the questions we will be looking in class, and please someone remind me how I can show you to find the theoretical probability, especially for scenarios of weather and so on. So take a look at these questions. Make sure you feel comfortable with them. See you in class, everyone.